Hi, Philip here. In this video, I'm going to introduce the basic tools of circuit analysis. And I'm going to try to keep it as short as possible. For some examples, I suggest you look at my homework preview for chapter 28. I'm also going to focus primarily on resistor circuits, not circuits involving capacitors, as I mentioned as briefly in passing. I'll make a separate video on how to deal with capacitor circuits, because they're in some ways more interesting and mathematically a little bit more complex. Let's start with the basic symbols that you're going to encounter when you analyze circuits or try to draw them yourself. So the basic symbols that we have, most of them are fairly intuitive. We just have a basic piece of wire. And really, it's going to be like a long line, right? This is my wire. You can go around corners. If you have a wire that splits into two, this is a junction. And it just means that if you are an electron traveling along the wire, you could go this way or the other way. Sometimes you see junctions drawn with a sort of dot here, but I think that that's optional. Right, so sometimes you see it this way, sometimes you see it this way, same thing. If you want to have two wires crossing, so this thing here means that the two wires are crossing and they're touching. There's a junction here. So if you're an electron, you can sort of have a choice of three, at least in theory. Now, if you want two wires crossing that don't touch, you draw it something like this. Here, and then you put a little sort of hoop around it. Right, we have to draw those wires in 2D on paper. You can imagine it sort of looks like you're hopping over the other wire. So in this case, wires are not touching. This is the basic wire. Next thing you might find in a circuit is a switch. And a switch we draw like this. This means the switch is open. If it's closed, it's just like this. And switches they don't do anything. They're either open or closed. So it's really like if it's open, it's almost like there's no wire there. And if it's closed, then the switch kind of doesn't exist. It's just a wire. Right? So a switch is really a way to draw two different circuits where the only difference is that this wire exists in the one case but doesn't exist here. Let me give you an example. I'm over here. Imagine, so this is the battery. I'm going to come to it in a second. And then maybe I have a resistor here. And I go over here and I have a second resistor here. Then I have a switch here. This is my switch. If the switch is open, it's like this whole thing just doesn't exist. It doesn't exist because as an electron could never go through there, it just can't go anywhere. It's like a dead end in your circuit that doesn't do anything to your circuit. If, on the other hand, the same, if the switch were closed, draw it again. It's a very messy circuit. If the switch were closed, it really just looks like this. Then the switch essentially isn't there. It's just like as if there was a wire here with a resistor and a wire here with a resistor, and I connect it here and here. So if I draw a switch, I'm really kind of drawing those two circuits at the same time, and I'm saying, is the switch open? And it's like this piece doesn't exist because it's not a path for electrons to go down. Or is it closed, in which case this piece doesn't exist. Okay, so the next piece that we're going to need is say a battery. So battery, we tend to draw like this. Sometimes you see it drawn with the same thing double. But it's always one side that ends in a long line and one side that ends in a short line. And the shorter line end has the lower voltage, the longer one is the higher voltage, and you can think of these as sort of elevators that take you from a low voltage up a fixed number of volts to a higher voltage. We'll deal with that in a moment, but it might say something like 9 volt. That suggests that this is 9 volt less than this. So for example, this might be 15 volts, and this would be 24 volts this side. Or it could be 0 and 9, or minus 100 and minus 91. But what it's telling you is this elevator takes you up from here to here by 9 volts. The next piece we're going to need is a resistor. In the resistor, we're just going to draw like this. I don't know if there's a fixed number of spikes you're meant to draw. I just draw like 3 or 4, something like that. It'll be fine. We know what it means. This is a resistor. And I'll talk about how they work in a minute, but you can think of them as kind of a thin piece of wire where the electrons have a hard time getting through, so they use up some of their electric potential energy as they go from one side to the other. And that energy gets released in the form of heat. The resistor might get warm or light if it's more like a light bulb, for example. How does the potential difference from here to here relate to the current? I'm going to come to that in just a second. Another thing you're going to see in circuits are light bulbs. Light bulbs look like this. This is the common way to draw them. And in many cases, you just pretend they are resistors. They are, in a sense, a type of resistor. Except they emit at least part of the energy as light, which is why they're light bulbs. But it turns out there are some subtle differences that if you run a high current through them, they get hot, and that actually changes their resistance, unlike ideal resistors. But I'll talk about that in just a second. And the last piece we're going to need for our purposes is the capacitor. And that looks like this. Looks a little bit like a battery, but except the two plates, right, are kind of the same size. So imagine this is like 2 plates of a parallel plate capacitor. It's actually kind of similar to how we've sketched capacitors in the past. I just said that was the last one. I lied. There are 2 more, namely devices that measure voltage differences and currents. So a voltmeter, you draw like this, that measures voltage, and the way it does it, imagine it has sort of 2 ends. We hook up the different points in the circuit. Maybe here, maybe there's a resistor here and a light bulb, right? That looks something like this. So we hook up this with its sort of two arms, 2 probes here and here, and it'll measure the potential difference, like how much higher is the potential here compared to here. Be a voltmeter. And then to measure current, and current is how much charge is flowing through a point per second. We have an ammeter. The ammeter sort of sits in the wire, kind of like a little, imagine it's a gate, and somebody next to the gate who counts the number of electrons passing through. This is an ammeter, and it measures current. Right, so voltmeter measures voltage, ammeter measures current in ampere, the same as an amp, the unit of current. I think that's where ammeter comes from, though I'm not entirely sure. Alright, now how do I draw circuits? Let's just have an example. Imagine I give you a bunch of wires and some light bulbs in the battery, and I ask you to hook those up. So, if you literally drew, like you take a picture, and you drew that your setup, what you see as circuits, it might look something like this. Maybe there's a resistor here, it goes like this, maybe like that. But then there's a junction here, and then there's a resistor here, and maybe this loops over this one, and then there's another resistor here, like this. Right? That's kind of what your setup might look like if you've got a battery and 3 resistors, and you sort of hook them up in some way. That's messy, and that's not how we draw circuits. That's what a real circuit, in a sense, would look like if drawn in symbols. In a circuit diagram, we only care about how the wires are hooked up. So, I see, okay, it's a battery that reaches a junction. Let me draw it like this. I draw it to leave space, to draw it so I've got space on the paper to draw it in a sensible, clear way. So this splits into 2. Maybe one goes this way, one goes this way. There's one resistor here. This is this path here, and that's going to go back to the battery, right? Following this path here doesn't do anything else except go back to the battery. I'm just going to draw it like this. There's going to be a junction somewhere. I'm just going to put junction down here because I anticipate that the other wire is going to go back there. So this wire here, following this one, there's one resistor. This doesn't do anything. I don't need to have it crossed. It doesn't matter. It doesn't change anything about the electrons. The electrons going through the wire, they can't tell that you're going over the top of another wire. So there's 2 resistors here, so I might just draw it like this. Here's 1, Here's 2, and it's the same circuit. Right? This here you can see much more easily what's going on. This is a mess, much like a real circuit would be. Right? Although even when you build real circuits, say if you had a physical lab in a real lab, right, building some circuits, there might be a total mess. You can do what you can to keep things clear, but it's never going to look as neat as this, and that's okay. But we still draw it like this because it makes it easier for us to analyze. Now, how are we going to understand what wires do? So wires, in our case, they're ideal. So let me use a new paper for that. So wires we think of as ideal. Wires are considered ideal. What does that mean? It means they have no resistance. That is not realistic. Real wires have resistance. It's just their resistance, meaning their sort of hindrance to current flowing, is very, very small compared to, say, light bulbs or these so-called resistors. So it's an approximation to say that these wires are ideal. What that means is, if you go along a wire, there's no electric field in the wire. It's almost a sort of electron highway. They just shoot along unhindered, not losing any energy. No electric field in the wire, and so no potential difference between any 2 points along the same wire. I'm going to be a bit more explicit in the same uninterrupted wire. When I mean uninterrupted, I mean you don't have a light bulb in the way. If you have a light bulb in the way, it's no longer true, right? So let me draw another example just to illustrate this. Here's a battery. Let's say here's a light bulb. Right, here is another light bulb, and this one goes back here. So what I'm saying is that this whole area here, it's just wires. You don't go through anything else that has 1 voltage. It's at the same voltage. You can think of it as the same altitude. If you take an analogy with walking along heights, along a mountainside, this is a path that takes along the same altitude. Now you might be going down, right? The battery took you up, like a sort of elevator or a ski lift or something, and this takes you down, maybe some rocky path down the hill, but then you're going to be at a different voltage over here. Let me indicate in a different color. If the color coding can be helpful, you've got a confusing looking circuit, right? All of this segment here is at the same voltage. Let me actually expand my circuit a bit. Let's imagine I've got a junction there, maybe a resistor here. Well, what is this telling me? That because this is just wire, all of this is at the same voltage. Different from the blue one, right? But any point here is the same voltage as this. So you only ever get voltage changes, kind of changes in the altitude of your path, when you pass through an object, such as a battery, or a light bulb, or a capacitor, or a resistor. Realistically, because wires have a small resistance, there will be a very gradual change. There will be a very small, sort of very gentle downhill path. Downhill meaning lowering the voltage as we go, ever so slightly. The big chunk of it would still be in the light bulb or the resistors. But then here again, it won't be perfectly flat. It won't all be perfectly at the same voltage. So maybe if this is at 10.9, then this piece here over here would be like 10.86 volts, something like that. These are just examples of non-ideal circuits. In our case, we're going to assume our wires are ideal, so that they're really all the same voltage. Okay, so now let's figure out what do light bulbs and resistors do. So a resistor you can think of as just a bunch of, if you go with the path analogy, there are a bunch of rocks in your way, right? The path is rocky, there are trees that are in your way, that have fallen over, something like that. And if you want to use a traffic analogy, the cars go along those paths, well, there'll be a like construction there. It slows you down. Now we can do experiments where you apply a potential difference. So for example, you could do an experiment where you hook up a battery to just a single resistor like this, right? And the battery is going to create a certain voltage, so this end is going to be higher than this by a certain amount. I might be able to change it. So with my voltmeter, right, I couldn't measure this. Remember, the voltmeter has these two sort of feelers, where it says what's the difference between here and here. And then you can measure the current through this. So if you plot that, I is the symbol we're going to use for current, against the voltage across the resistor, voltage difference across resistor. It doesn't matter if this is 100 and 110, or 50 and 60, or 1,000,000 and 1,010,000, right? Only the difference matters. In all those examples, it was always 10 volts different. This is the current through the resistor. How many coulombs per second worth of electrons are going through this resistor. If you plot this, you can do some data. Well, if you put no voltage across them and get no current, you plot this and you find you're going to get a straight line. Now you can do this experimentally. Kind of one of the first experiments that you might do when you have circuits. Maybe some of you did that kind of example in high school or middle school. Okay, so that means we've got a proportionality, right? The I is proportional to delta V, and we can write the proportionality constant. And the way we tend to do this is we're going to say it's this potential difference divided by the resistance. So with the analogy of mountains and walking down a mountain, the current, meaning how many of you are going to come down the mountain, depends on how steep it is. The steeper it is, the bigger the drop off, the more force you get pulled down, and divide by the resistance how many rocks are in your way. Or maybe the better analogy would be, imagine you've got a stream of water that runs down a mountain, like a little brook. How much water is coming down? Well, it depends on how steep it is, and or what rate is the water coming down, how steep is it, and how many rocks are in your way. It's not a perfect analogy, but I think it helps you visualize kind of what's going on here. Resistance has it kind of in the name. How hard is it, right, to get through? Higher resistance means less current with the same voltage. Now, if you have a light bulb, this, by the way, has a name. I'm going to call this Ohm's law. And it's going to be very important. We're going to use it all the time in resistor circuit analysis. If you've got a light bulb, but this was a resistor here. If you've got a similar situation where you've got a light bulb, and I'm not going to draw the voltmeter, to pretend we can just measure the voltage. It looks kind of the same. So it sort of starts out the same, but as you increase the voltage more and more, it actually flattens off. So what's that telling you is that you need more and more voltage to get an increase in current. Or in other words, it looks as if the resistance is increasing. If we sort of try to say, let's apply Ohm's law anyway, then it says that R isn't constant, but the resistance is increasing. Right? The current just doesn't want to go up as easily anymore as I add more voltage. Why is that? Because light bulbs get hot, and hot wires, if you were to zoom in on the wire, it means little particles, the little atoms inside it, they jiggle a lot more back and forth. And so electrons want to pass through, they're more likely to bump into it. We're going to study the models for what happens on the inside of a wire as electrons try to get through it in more detail, and very soon in chapter 27, which, if you remember, we're doing after chapter 28. So we're going to study the inside of a wire, for example, the inside a filament of such a light bulb, in more detail in the near future. If you have a low voltage across your light bulb, though, then it's pretty much indistinguishable from this sort of ideal resistor. Resistors actually also get hot, and their resistance will increase slightly. So even though they're not perfect, it is a lot better than light bulbs. Okay. Now, the other component that you might come across is a capacitor. Right. So this was light bulbs, resistors, light bulbs. We're going to have capacitors. Of course, there are other types of things you could have in circuits. If you take an electronics course, you'll meet lots of them, but for our purposes, we're going to stick to these ones. And so a capacitor, remember, looks like this. It's like a parallel plate capacitor, even if the actual capacitor that you have is not a parallel plate capacitor. Right? We still use the symbol, and hopefully you remember, and if not, you can look that up right again, is that capacitors can hold charge, so it might look something like this. And if they do, then there is a potential difference across them. And for a capacitor, we did those calculations. The charge is proportional to the potential difference, and the constant that relates them is the capacitance. Remember that the capacitance was defined as the charge per voltage across. The applications of those are, for example, you charge it up by hooking up to a battery, then it stores the charge, and then you can suddenly release the charge. For example, if you want to have a camera flash, like suddenly a very bright light for just a second, that means you're connecting this up, you're allowing the charges to leave the plate, and you put a lot of current for a very short amount of time until the charges have left the plate. So you can use a low voltage, such as that from a battery. You know, it's not that much power is going to come out of it. It only creates maybe 1.5 volts or something. You use it to charge up a capacitor, and then you can release a lot of energy in one go. And for example, the flash of a camera is a good example of that. It also allows us to create certain time-dependent processes, because it takes a certain amount of time to charge up the capacitor, and we can use that, and that can then be used in conjunction with, let's say, resistors, or something called inductors, which we're going to come to very near the end of the course, to get, say, repeated behaviors, such as the windscreen wipers of your car. You turn them on and they go. Like, how do they know how long to wait? Well, that's done with circuits involving capacitors as well. And we'll look at that kind of behavior in more detail later on. Notice that all those objects, capacitors, light bulbs, resistors, they always have a potential difference across them. It's just they're different results, right? If there's a potential difference across a capacitor, it means it's holding a charge, but there's no current flowing. Well, there could be. That would be changing the charge. I'll talk about that more when I talk about capacitor circuits in a different video. In light bulbs and resistors, having a potential difference means there is a current flowing, and the current isn't changing. So there's a continuously charge moving from one side to the other, as long as that potential difference is maintained. The way to maintain it is, for example, by having a battery there. So let's now look at the rules of analyzing any kind of circuit. And as I said, I'm going to do examples elsewhere. I'm just going to summarize them and explain them very briefly. The rules of circuit analysis. These are sometimes called, at least some of them are called the Kirchhoff rules, but really they just come from our understanding of what voltage and charges are. The first one is the charges, the amount of current entering a junction is equal to the amount of current leaving it. Okay. That should seem fairly obvious. Why is it obvious? Because if you're an electron moving along the wire, right here you are, little electron E, and you come along, you get to make a choice. Do you go this way? Do you go this way? Of course, it's really random processes in how you're bouncing around inside the wire, but you can imagine you're making a choice here. And now if you haven't got one electron, you've got, 12 electrons. Well, some of them might go this way, some of them might go this way, but if 12 electrons come along here every second, then 12 electrons are going to go out here and here together every second. So if, say, current 1 comes in, current 2 goes out this way, current 3 goes out this way, then I1 equals I2 plus I3. This is called the junction rule. It's very basic. It's really just saying charges don't get created or destroyed, or they don't build up anywhere in the wire. If they did build up, they'd create an electric field, because there would be a net charge right there. This is the first rule. Very basic, but very useful. The next rule is to do with understanding voltage, and what it says is that if you imagine you walk along the circuit, you walk, could be with your finger on the map, right? You walk around a circuit, sorry, not a circuit, circuit is the setup, a loop, and end up where you started. If you do that, then your then the net voltage change, or total voltage change, is 0. Let's look at a simple example of that to make sense of this. So here's a simple circuit with a resistor, and if this is 9 volts, the battery takes me up 9 volts. Well, this is a loop. I might be going around a loop like this. I walk, right? And what the law is saying, well, if you walk all the way around this loop, you got to go down as much as you go up. So your net voltage change is 0. So here we go up plus 9 volts, which means because wires are perfect, they're ideal, there's no change here, means here we must be coming down 9 volts. Very simple. Of course, it gets more interesting when you've got circuits where you've got multiple loops to choose from. So for example, if you have a circuit like this, with a light bulb and a resistor, then it would be true of this loop here. It would be true of the big loop like this, where you go around this way. It would also be true of this loop here. You go down the circuit, the loop either way. For examples of actually applying that, there are some subtleties here. You have to be very careful in the application to get the signs of the voltage change right. I do an example of this in the homework preview, where I analyze problem 52 from chapter 28. But the sort of rule of thumb is that if you go with the current, then batteries will take you up, resistors and capacitors will take you down. The next rule we need to analyze resistor circuit is nothing but Ohm's law, which we already know. It says that current is equal to potential difference divided by the resistance, and that's applied to each resistor. And for capacitors, which I'm not going to talk about anymore right now, you have the relationship between the charge in the capacitor and the potential difference across it. So those three rules, and the first two together are called the Kirchhoff rules. Those rules together, including Ohm's law, will give you a large number of equations for any circuit, right? Especially if it has junctions and multiple loops and multiple resistors. So mechanically, you could just write them all down, and doing that will, together with Ohm's law for each single resistor, will give you enough equations to solve for all the unknowns in the circuit that you're given. Right? So it's a very mechanical process. No matter how complicated, you just get a very large number of equations. Like for every junction you get one. For every loop you can think of you get one. For every resistor you get one. And then the rest is just algebra. Combining them, the algebra is very simple because nothing is squared or, square rooted or anything like that. It's all just linear dependencies. But it can be lengthy to actually then eventually calculate the one thing you want to know. There is one other small piece that I haven't talked about yet, and that is the power output of a resistor, say. And the power output is, I'm just going to write it down, P for power is the current through it times the potential across it. Why is that? Well, the potential across it gives me the... If you're an electron, you're moving from one side to the other, you lose a certain amount of potential energy. Potential energy lost per coulomb, right? Because that's how voltage is defined. So you go from a high voltage to a low voltage. You imagine sort of the mountain view, right? You go from one point up here to a point down here. You've lost a certain amount of potential energy. And I can write down, if it's gravitational, what's the potential energy per kilogram that I've lost? Would be equal to GH. So this is the potential energy lost per coulomb, and when I say lost, I mean converted to things like light and heat. Possibly other things, but mostly those. Mostly heat, actually. And then what's the current? The current's telling me how many coulombs I get through the thing per second. That's what current means. So, how much energy is put out per coulomb? How many coulombs I get per second? It gives me the energy per second. So I mean by power. Energy per second. Okay. Now for the last part of this video, I am very quickly going to sketch two shortcuts to analyzing resistor circuit. And I'm going to stick with resistor circuit here just because they are they're easy enough to analyze that I can do it in this video. For capacitor circuits, I'm going to make a separate one. Alright, so there are essentially two sort of tricks or shortcuts to analyze resistor circuits. They just follow from what we've already talked about. They concern resistors that are in parallel or in series. Resistor circuit analysis. So the first one is when I've got two resistors, they are like this. This could be, I don't know where this comes from. It's just part of a circuit. They've got resistances R1 and R2. Then, well, so say there's a certain total potential difference across them, delta V total. Right? What is it telling me? Well, in terms of delta V1 and delta V2, delta V total is the sum of the two, right? Because if I go down a certain amount here and down a certain amount here, total I've gone down from here to here, and potential is just the sum of those two. So let's write it down. Delta V total is delta V1 plus delta V2. Now we're going to apply Ohm's law. Right? Delta V1 is I, the current through this thing, times R1. This is going to be the current through this thing times R2. The crucial insight here is because there are no junctions, no junctions, so there's the same current. And we call this current I, right? The voltmeter itself, technically it creates junctions, but no charge can go through here because the internal workings of the voltmeter is presumed to have an extremely high resistance. Essentially says, no, you can't go through here. It's like this path is blocked. I'm just feeling the difference between here and here. So I get this equation here. I can factorize it, R1 plus R2. So now you can see that this is really Ohm's law. Current times resistance, where the total resistance is just the sum of the two. R total is R1 plus R2 if in series. In series means if you're an electron, you have to go through both of them to get to the other side. The other example, so this is our first shortcut. The other example is going to be when you have resistors in parallel. So it might look something like this. And in parallel is just a term we use to mean this kind of setup. What does it mean? It means if you're an electron, you come here, you go from one side to the other, you have a choice. Do I go through the one or do I go through the other? But you're not going to go through both, and you are going to go through at least one of them. So you're going to go through exactly one of them. These are in parallel. So what's the same here? We don't know, right? The current through this one, let's call it I1. The current through this one, let's call it I2. There's no reason for them to be the same. But the current that comes in the first place, we know from the junction law that I total better be equal to I1 plus I2. Because any electron has to go this way or this way. So if you're counting them here, you're going to get the same as adding up what you would count here and here in terms of electrons passing you. Of course, when they recombine, you're going to get I total back. So let's use Ohm's law here. I have that I total is equal to I1 plus I2, and we write it as delta V1 over R1 plus delta V2 over R2. But crucially, the voltage difference is the same, right? Because if you start out on this side, remember all this is the same potential. All this is the same potential, right? You go from blue to purple. So however far I'm going down over here, I'm going down the same here because those 2 points are the same potential. Those 2 points are the same potential as each other. So there's really only one delta V. So I have that I total, the total current is by junction law, it's this. I can rewrite it as this. There's only one delta V, which I can then simplify. Now, if I were to write this as delta V divided by R total, right? So you can ask like, what's the combined resistance? We can see that this thing here is equal to 1 over R total. So I find that 1 over R total is 1 over R1 plus 1 over R2. Of course, this generalizes further. If I get 3 resistors, I'd add 1 over R3, 1 over R4. Similarly, for the in series one, the same logic applies. If I had 10 of them in series, you could electron go through one, next one, next one, next one, next one, while I just add the individual resistances. So what does it mean? It means essentially I could imagine if this is part of my circuit, I am going to cut out this piece here and replace it by a single resistor that has this resistance, and it will change nothing else about the circuit. So notice that if they're in parallel, right, the overall resistance is going to be lower. You can plug in numbers to test that. Right, so if R1 and R2, say, are each 2 ohms, 1/2 plus 1/2 is 1. So 1 over what is 1? Okay, 1. Then the combined resistance would be 1 ohm. So 2 ohms makes 1 ohm, whereas 2 ohms in series makes 4 ohms. Think of it again maybe with the road going through construction analogy. If your car, you have to go through this construction, and this construction is going to slow you down a lot. Whereas if it's like this, then all the cars coming, yes, there's construction here and here, but at least the cars get split into 2, not necessarily evenly. I want to emphasize that, right? Just that the sum is equal to the total current. Not they don't have to be the same as each other. So it gets split up, so it's kind of more bearable, right? The overall resistance is less than if you just had one construction and everybody had to go through that. At least some of the cars can go a different way, but they also have construction, but it sort of lessens the load a bit. Okay, so those are the basic tools. Although those shortcuts, in a sense, are even things you don't strictly need, because you can just apply those rules I lined out earlier, the Kirchhoff rules and Ohm's law. Those will solve you all resistor circuits you might come across. The rest is practice. Some circuits cannot be analyzed with the shortcut method, namely when you've got, say, more than one battery in different places, for example. Then you will need to explicitly use the loop law and the junction law. But in many other cases, when you only have, say, one battery and a bunch of resistors in some arrangement, you can usually just simplify this circuit step by step using the shortcut rules. Which one is faster? It depends on the particular problem. With some practice, you'll get to figure that out. So I hope that helped. I hope that sets you up for success in the homework and mastering this topic. Check out the homework preview videos where I go through some examples. And then, as I said, the rest is practice. Circuits is really more like these little puzzles that you can solve in these very mechanical ways. Once you've got a few under your belt, there'll be no problem at all.